Hello there. So this is video number 2 of section 3.3, and this will be dedicated to one single application of Cramer's rule, which we will talk about in a second. So I just want to go over a few things sort of leading up to what this application is going to be. Well, actually, we kind of have it on the board already, but so we're going to let A be an invertible n by n matrix. And we're going to express its inverse in the following notation. So here I'm going to let x sub 1 through x sub n just be the columns of my matrix A inverse. So notice that now this product, A times A inverse, of course, is equal to the identity matrix. And so notice that specifically, we can rewrite A times A inverse as A times x1, A times x2, and so on. Right, so this here is another way of expressing this, just sort of in a different notation. Right, but this means that A times x1 has to equal the column vector e1, and so on. And so this is true for every index, and so we get this relation between the columns of A inverse and the matrix A. That is, A times the jth column of A inverse must be the solution to the equation AX is equal to E sub j. And remember, these columns of the identity matrix, so E sub j is just the vector of length n of all zeros with a single 1 in the jth entry, right? So E1 would be the vector 1, 0, 0, 0, 0, 0. So since we have this knowledge about the columns of A or A inverse and the matrix A, we can apply Cramer's rule. Because remember, Cramer's rule gives us the ith entry of this vector x sub j. And so if you think about then how A inverse is laid out, I can use Cramer's rule to solve for the ij entry, which we will denote x sub ij. So this is x sub ij of A inverse. And so this entry here, x sub ij, is the entry appearing in A inverse that is in the ith row and jth column. And so by Cramer's rule, we know what x sub ij is equal to. It's just the determinant of the matrix where I replace column I in A by the vector E sub j and divide it by the determinant of A. So that was a lot of indices I and j. Keeping track of these, I think, maybe is the hardest part of this application. Well, for me at least, it's the most confusing part of this application. But so remember, the entry in the ith column and jth row of A inverse is equal to the determinant where I replace the ith column of AI. So ith row, jth column of A inverse, I replace the ith column of A with the standard basis vector E sub j, and then divide by the determinant of A. This is much easier to see doing an example. I think we can just sort of put all the indices in place and kind of start to work things through. All right, so what we want to do here is find the 2, 1 entry of A inverse. So ultimately what we want, we need the first determinant of A. Then we need the determinant of A sub 2 E1. And so notice again here, I'm going to replace the second column of this matrix with the standard basis vector E1 in R3. And then I will get x sub ij. All right, so first things first, the determinant of A. So this is equal to, well, I'm going to expand across the first column, I think is what I did in my work. Yes, across the first column. So I'll go a little quicker this time with the determinant calculations. So notice, since the third entry of the first column is 0, I only have to worry about these two terms. And so that gets me 2 minus 1 times 1 is 1. Here I get minus 4. And this should be negative 3. So this part of it isn't super important. Well, it is, of course, but so the determinant of A is negative 3. All right, so if we want to find now the determinant of A sub 2, where I replace A sub 2 of E1, well, first we should probably figure out what is A sub 2 of E1. So again, this is going to be the matrix where I replace the second column of A by the standard basis vector E1. Just like that. And so what's really nice about this is that to find the determinant of this matrix, all I have to do is just expand down, and this is going to be true in general whenever we're finding the values of these matrices for all I and j. I replaced one of the columns of A with a very sensible column to expand down. So notice, no matter when I do this, I'm going to now have a column of all zeros and a single 1, right? Because this is the column I replaced. And so I'm just going to expand down this column, and my determinant is just going to contain a single term. Because this is just going to be negative 1, right? Because this is in the first row, second column. So it would be negative 1 to the 1 plus 2, which is just negative 1, times the determinant of 2, 1, 0, 1. Well, and so that's just equal to 2. And so the second row, and so this is equal to 2. And so the second row, third column entry of A inverse is equal to negative 2 over 3. And so I actually shouldn't say, so this is the determinant of, I made a slight mistake here. This matrix isn't equal to its determinant, but this is the determinant of this matrix, which is equal to 2. So sorry about that. But the determinant of this matrix is equal to 2 by using cofactor expansion across that first or second column. All right, so keep this in mind for a second, and I want to point out a larger pattern that sort of we can extract from what we just did. So notice that what I got by replacing the replacing the column by this standard basis vector was actually just the cofactor, right, that I would have used in calculating the determinant, right? Basically, what that means is I just got the determinant of this submatrix where I deleted column 2 and row 1, so this submatrix here, multiplied it by the appropriate 1 or negative 1, depending on which row and column it corresponds to. And so notice that the determinant of this matrix is actually just a cofactor of the matrix. So it turns out that for all I and j, the determinant of the matrix where I replace column I by the standard basis vector E sub j is just negative 1 to the I plus j. times the determinant of the matrix. Well, what happened, I deleted column 2, row 1. So where I deleted column 2, row 1. So where I delete the jth column, jth row, ith column, which is just the cofactor c sub ji. And so like I said, this is where the indices get confusing to me, because if you notice here, or they always get confusing to me here, because if you be really careful here, this I and j switch from here to here. So like I want it to be ij, but it's actually ji, right? And that's because we delete the jth row and ith column. All right, so all of that out of the way. So this means we actually now have a slightly easier way of representing the ijth entry of the inverse matrix. It's given by c sub ji over the determinant of A. And so remember, this is the entry x sub ij. And so again, notice the switch in indices here, and just be very careful about it. I think it still gets me every time keeping track of it. All right, and so this actually leads to, I really want to say a nice formula for A inverse, but like even your book admits that this is a very suboptimal way to compute A inverse. So this means that I can compute A inverse for any n by n matrix in the following way. So it's the matrix 1 over determinant of A, where each of these entries here are just the corresponding values c sub ji, which are computed in this way. So what's sort of nice about this, as we'll see when we do an example, is that because we've sort of figured out what's going on here, we're actually able to get rid of having to worry about replacing this, right? Because all the cofactor c sub ji is just this determinant where I've deleted row j and column I. And so I don't have to worry quite as much about replacing this vector each time like I did here. I can sort of skip a step if I'm going to compute the inverse this way. Generally, if you're computing the inverse just for the sake of computing the inverse, it is not always optimal, where this type of thing, using Cramer's rule in this way, can come in handy. Sort of as we saw with like solving systems of equations in the last example, is some more theoretical applications. But also, what this does nicely is, I think, gives you sort of a way of estimating how much like small perturbations in your original matrix A will affect your inverse matrix, because you have this sort of nice closed formula, so you don't have to do a ton of row reduction steps each time. But of course, if you're just calculating a single inverse, this is definitely not the optimal way to do it. But it has its uses again. So this matrix here is called the adjugate of A. I always want to call it the adjunct, but it's the adjugate. And so we abbreviate it adjugate of A. And so we'll define that officially. So the matrix right there is called the adjugate of A. And we denote it just like I did here, ADJ of A. And so we get this nice theorem then, which we've sort of already stated, but we'll state again just for to definitively define it as a theorem. If A is invertible, then its inverse is just equal to 1 over its determinant times the adjugate. And so you might be able to see how, like, again, if we're trying to compute like small perturbations in a matrix or trying to see how this affects it, because these small perturbations could be very quickly calculated sort of using this method. And so, I could certainly see sometimes where having this way of calculating an inverse would be more optimal than having like the row reduction way. But like I said, you can even read in your book. The book is even like, I think, this is not the way to do it. And so sometimes whenever, like if even the book admits it, sometimes it's like, well, why are you teaching it to me? But anyways, so I just want to end with an example. You will see through this example how inoptimal this this process is. So we're going to work with the same matrix that we worked with earlier in this video. So we want to use Cramer's rule to find A inverse if A is again, the same matrix we worked with before. So 1, negative 2, 0, 1, 2, 1, 3, 1, 1. All right, so we already know that the determinant of A, since we calculated it earlier, is negative 3. And so right off the bat, we know that A inverse is equal to negative 1/3 times, and are you ready for this? C11, C21, C31, C12, C13, C22, C32, C23, and C33. And why does your book, after teaching you this, recommend not using this method? This means we have to calculate 9 determinants. And you know what? I sort of was on the fence about it, but I'm just going to go ahead and calculate these. It'll be good determinant practice. So yeah, we'll jump right into calculating some determinants. So C11. So again, I want to do negative 1 to the 1 plus 1 times the determinant of the submatrix where I delete row 1 and column 1. And so working that out, I get 1, 2. Next we want to do C12, negative 1 to the 1 plus 2 times the determinant of negative 2, 1, 0, 1, which is equal to 2. 3, C13 is equal to negative 1 to the 1 plus 3, which is 4, times determinant of negative 2, 2, 0, 1. And this is equal to negative 2, 4. C21 is equal to negative 1 cubed times 1, 3, 1, 1 is equal to 2. Probably going to need a little more room here, so I'll bring this down here. 5. Make it a little lower. 5. C22 is equal to negative 1 to the 4th times the determinant of 1, 3, 0, 1 equals 1. 6. C23 is equal to negative 1 to the 5th times 1, 1, 0, 1 equals -1. 7 C31 is equal to -1 to the 4th times 1, 3, 2, 1, which is equal to -5. 8 C32 is equal to -1 to the 5th times 1, -2, 3, 1 equals -7. And finally 9 C33, which is -1 to the 6th times 1, 1, -2, 2, and that's equal to 4. So 9 determinants of submatrices of A. Doing this, first actually doing this, we know that the adjugate of A is equal to the matrix 1, 2, -2, 2, 1, -1, -5, -7, 4. So this matrix here is the adjugate of A. And then a inverse, which is equal to -1/3 times the adjugate, is equal to -1/3, -2/3, 5/3, -2/3, 1/3, 7/3, 2/3, 1/3, -4/3. And that is Cramer's rule. Well, one application of Cramer's rule. So yeah, so maybe not, as you can see, the most efficient way to calculate a determinant, or not a determinant, an inverse, but it's a good tool to know that you have, especially if one day you're going to be programming computers to do this. A computer could probably tackle all of this relatively quickly. And again, well, maybe not the most efficient way to just calculate an inverse if that's all you want. You can learn other things about the inverse by knowing many different ways to calculate it. So, how to calculate an inverse using Cramer's rule.